Here we.
So I'll just say a quick intro and thanks to Jonathan Park for joining us today all the way from Penn State. What year are you now in the graduate program?
I'm a fourth year in the program.
So nearing the end of a PhD in the quantitative area, working with some statisticians who developed the method that we're going to hear about today. So we're very excited to get all the nitty-gritty details, and we're happy to have you here as long as you're willing to stay and chat. So so thanks again, Jonathan, for joining us.
Yeah, absolutely. I was saying earlier that like once Zach asked me and reached out, I could not possibly say no. So I'm from Penn State. I work with Peter Molenaar, who is Katie's advisor. And I also work with Seaman Chow. And so I'm really definitely more in the methods area. So I think Zach clarified in the email that both he and I are not neuroscientists. So certainly there'll be examples, especially when we get to the HRF GIMME, where I am completely out of my depth and I can just kind of explain how it works. I saw from the syllabus that I was sent that you guys read Katie's 2012 paper as well as Teague's confirmatory subgrouping paper. And you can also see at the top, there's like this legend of the things that I'll be covering, and you'll see that confirmatory subgrouping is one slide. And the reason for that is that the subgrouping, so just the regular SGIMME, kind of has a lot of development in it. And the idea is that by covering the SGIMME portion, everything else should make sense. Like when you go into other extensions, kind of having the foundation of how SGIMME works really helps in terms of understanding everything else. I would really say that it's probably out of the flavors, so to speak, of GIMME, it's definitely like the most complicated one. So then going with that explanation and then moving into the confirmatory subgrouping should make it relatively easy. But I will caution that it gets dense, and there'll be times where I just hand wave some equations. So yeah. Whenever I like talk about things, I like to give some broad goals. So we'll be talking really briefly about the history of GIMME. I always dislike when people talk a lot about history. So it'll be relatively short. It's just a couple of slides to kind of give an idea of like what problem GIMME was designed to solve. And then we'll go into the equations and stuff and hopefully really flesh out how it answered those questions or resolved those issues. And then we'll talk about the model foundations, right? So like GIMME is an algorithm, it's a procedure for fitting models, but it's not in and of itself the statistical model. So we'll talk a little bit about like what the statistical model that underlies GIMME is and why we went with an algorithmic approach in estimating it. And then after that, we'll talk about GIMME itself and then its extensions. And then like, I totally, if people have questions at all, feel free to just stop me. I can't guarantee that I'll have an answer, but I'll give it my best shot. And if there are questions that I can't answer, I'll jot them down and I'll definitely like follow up in an email. So this slide is really verbose because I didn't write it, but GIMME had several goals kind of on its outset, right? So the idea was that a large body of work has been had been showing that kind of temporal processes are not homogeneous. The ways in which people change over time are not the same, right? So even something as simple as growth can be used to show like how heterogeneous people are, that we reach different heights and we reach our max height at different times in the developmental time span. And so to assume that people change or undergo their change processes using a similar or identical model just did not seem tenable. And in earlier research where we would just aggregate data, this has been kind of noted in early fMRI research where we didn't really acknowledge that individuals existed. And so we would aggregate data across individuals and get like one map of the interactions between ROIs. Really drew into question, does that make sense? Is that like a justifiable way of modeling these people and these data? And kind of the biggest paper of the second bullet point was Peter's manifesto in 2004, which basically drew up these mathematical arguments that basically discussed how, unless you meet these strict mathematical assumptions, which are like the ergodic theorems, you shouldn't assume that the process for any given individual relates to the process of any other individual. And then further, in that last bullet point, basically, when you kind of aggregate across people, you can't really assume that that aggregate generalizes to any one individual either, right? So the group level model might not describe any of the individual participants. And I have some like really simple examples that I'll show in the coming slides that kind of show that. So really the broad goal of GIMME was, right, group level models are really useful. At the end of the day, if I have a bunch of n=1 models or models for each person in this room, it's not really useful other than to describe your own dynamics. So when it comes to drawing kind of broad ideas of, let's say, like how depression works or how suicide works, which is my area of study, it's not useful to just have the person-specific networks, because we need to have kind of generalizable and actionable patterns that we can identify. But if we know from past research that aggregating across people isn't the best way to do it, how can we do that? And so the goal of GIMME was basically to build the individual models first, and then find the common patterns in those individual change processes, as opposed to aggregating first and then trying to find a common process through that. And so like the difference is nuanced, but the results were quite different. And then obviously the last part was to also get kind of reliable person-specific maps. So Simpson's paradox is a thing, and this is related to the idea of aggregating data and why it's not kind of the best thing to do all the time. And so in this example, this isn't related to really any data that any people do, but we can imagine that the black dashed line could be the relationship between, say, typing speed and number of typos that someone makes, right? So there's a bivariate association, and people who are really good typists tend to make fewer errors, right? I don't think that's like a controversial thing to say. And then people who are really slow, people who are learning to type, aren't familiar with the keyboard, they'll probably type slow and make more errors. So at the group level, we'll see that there's this negative association between typing speed and the number of typos. But then within an individual, if I like stood behind you and just yelled at you to type as fast as you possibly could, you would make more errors than you typically make. And if I told you to type slower than you're comfortable with, you'd probably also make fewer typos. And so the within individual relationship is the exact opposite of the between person association. And so if we model kind of the group level trend, we would find literally the opposite of what's actually going on within people. To kind of highlight this more, this is a simulation that I did. This project actually is what got me involved with GIMME. Is if we ignore that people come in kind of heterogeneous groups. So I simulated these two subgroups in the center and the right columns. And what I wanted to show is that, yes, if we aggregate these people, the group level model basically averages out the positive and the negative connections between variables 2 and 3. So then our group model would say there's no association between variables 2 and 3, even though 50% have a positive connection and 50% have a negative connection. So really the idea of ignoring that and just aggregating people, pooling them together, really just doesn't seem tenable. So then this is kind of like the philosophy of GIMME, is how can we find group level trends from those idiographic or kind of person specific processes. I didn't realize how like pixely this image was, but hopefully it's not that bad. So on the left and the right, we'll see kind of a map using GIMME. So this is some of the results that you could find if you run GIMME on your data, which shows kind of the interactions between different regions of interest. On the left, using fMRI data, and then on the right, kind of affect data taken from like ecological momentary assessments or like daily diary studies. I'll talk about like what the dashed lines and stuff mean, but kind of on a broader scope. Basically, the bold black lines will indicate group level paths. So a bold black line from this looks like motor to the auditory areas indicate that there's a group level path. So across all individuals, at least a majority of them, this path seems to be there, right, for a majority of the individuals. And then the green paths indicate subgroup level paths. So when you run GIMME, you have the option to ask for subgroups. In this case, it did find subgroups, and the green paths were subgroup specific ones. And then finally, the gray paths indicate the person-specific paths, so paths that exist for an individual or a number of individuals, but didn't exist in a large enough number to count as the majority, to get fixed as like a group level path. And something that to kind of take away from this and related to the earlier point is that there's a lot of individual paths that aren't picked up by the group level model. And so there's so much like, oh, yes.
No, I didn't want to interrupt your last sentence. I also was wondering whether you set the thresholds as to what can be considered a subgroup, or whether it's done automatically based on maybe your sample size or what.
Yeah, so in Teague's paper, he talks about some cutoffs that are arbitrarily set. Unfortunately, there hasn't been a whole lot done in terms of automating the selection of the cutoff. But in simulations that Katie and our group here at Penn State has carried out, 75% seems to work, and that is the default. So if you don't touch any of the defaults in GIMME, it will set a default where the group level paths will be set if 75% or more people have that path. And then for the subgroup path, it's 50% or more of the individuals within the subgroup have to have that path. And generally that tends to work. It changes a little bit with CS GIMME, so confirmatory subgrouping, where with the subgroup paths, that's also set to 75%. And the reason for that is that since you have an a priori idea of what your subgroups are, you have more power, so you can be a little more strict on what counts as a subgroup path.
Thanks.
Yeah. I do have a link at the end of the talk as well to like some demos, so I can share these slides if anyone wants them after as well. This is just so much text. So we talked about the origins of the algorithm. I know that you all read Katie's paper with Peter in 2012. It was actually preceded by two other papers in 2011, 2010, all published in NeuroImage. And the 2010 paper, they basically established an equivalency between the vector autoregressive model, which is the model that kind of forms the basis of a lot of how we explore these kind of temporal relations among variables, with the structural VAR. And then the 2011 paper proposed the extended unified sum for looking at event-related data. And that's kind of carried forward into the HRF GIMME functions, which we'll talk about in a bit. So this is where I get excited. I don't know if other people get excited from this, but this is like my favorite part. So we'll start with the standard vector autoregressive model. I'm just going to call it the VAR. And in this case, you see that there's variables at the previous time point predicting variables at the current time point, right? So what this is what we call it is a VAR of order 1 or a VAR 1. And that's because we're only going back one step in time. So you can have a VAR of any arbitrary order. You can have VAR 2, VAR 3, VAR 4, whatever. In the case of GIMME, by default, it does VAR 1 models. So that's as far as I'm going to go and as far as I'm going to talk about. And what we see is basically for this bivariate system, we have the autoregressive effects, the effect of a variable on itself, right, at the next time point. And then we also have the cross regressions or the cross regressive effects where it's the effect of the variables on other variables at the next time point. Kind of something that might help kind of keep this in our heads. Typically when the autoregression is particularly strong and positive, so like let's say like a 0.8, we might call that indicative of inertia, is the term that we use in our area. And the idea is that when you're perturbed up, you tend to stay up. It takes you longer to come back to your baseline. So the idea is that activation in the previous time point is associated with kind of staying around that area at the next time point. Whereas if you have like a negative autoregression, like a negative 0.8, that means you have kind of a volatile cycle over time. So you can imagine like if at one point you're at a, I don't know, like a 5, then the next point you'll be much lower than that. And so you can imagine it as this kind of erratic cycle. So if that helps to kind of conceptualize it, there you go. In terms of the equation for the standard var, you really just have this vector of scores at time. So it's really just like V1 and V2 predicted by some regression coefficients matrix times the scores at that previous time point, plus some residuals. And the residuals actually in the var are really important for GIMME. This is kind of where the magic happens, so to speak. So we see that the residuals have a vector of zero means and a covariance matrix of psi. And I kind of touched on the first point, but var1 models the effects of the previous variables on the current time point. But this is where GIMME and kind of where we're going becomes really relevant, but processes that occur faster than the sampling rate are captured in those process noises. And the example I have here is that balloons appear to pop instantaneously. So this might take a bit of explaining, but if we have like a camera, if we're filming a balloon and I like pop the balloon, it'll look like it just popped instantly, right? But if I have like a high-speed camera and I pop the balloon, you can actually see that it takes time for the balloon to pop, right? You can see like the rubber contracting and all that stuff. And the idea is that if we have a sampling rate that is matching the dynamics, then we can model it with a var1 with no issue. But the problem is a lot of the time we can't sample at the rate of the actual dynamics, right? And this actually is the case with fMRI data, where we can only get the temporal resolution so small within like the boundaries of actual technology. And the rate at which the dynamics are occurring are still faster than what we can sample with fMRI data. And so what we're basically seeing is that a lot of the information that we actually care about is in this residual, right? So we can partition out the variance of the lagged effects, but getting into the dynamics of what's happening at a faster time scale would be kind of what we're really interested in. And so in those cases where we want to kind of extract it from the residuals, we can fit what's called a structural var. So this is kind of the exact same thing as a var model, but now you can see that there's this A effects matrix, which represents what I'll call the contemporaneous effects. So basically we just need to find a way. It sounds really easy, right? We just need to get A, and then we're done. So again, this is identical to the var equation, but now we have this A matrix. And what you can see is that while the phi matrix is multiplied against eta at the previous time point, the A matrix is multiplied by eta at the current time point. So really the restriction is that the diagonal elements of A have to be 0, right? Like a variable can't predict itself instantaneously because that's not how causality works. And that's really the only restriction. The other change is that the phi matrix is now restricted to be diagonal, right? So basically we're assuming that we are tapping into that extra information in the residual covariance of the regular var model. And so by doing that, we're restricting the covariance matrix of the structural var to be diagonal. And so then the question comes, can we actually model these contemporaneous effects? And the answer is yes. But prior to the 2010 paper, a common approach, and this is taken from econometrics, was to estimate structural vars using Cholesky decomposition. If you don't know what that is, that's fine. I barely know what that is. But basically, the issue with using Cholesky decomposition on the residual process noise of a var is that the direction of the effects depend on the ordering of your variables. So if I put a certain variable at the top, then that's going to point at all the other variables first before any other variables. And the fact that obviously you shouldn't allow your choice of ordering to affect the direction of effects seems really like a huge issue. And so to address this, Katie and pretty much everyone at Penn State is basically on that paper, but they constructed the unified SEM. There's also work by Peter Bentler that preceded this. So if you're familiar with your guys' quant psych area, Peter there also does stuff there. But basically, there's no unique solution when you use Cholesky decomposition. And so they wrote up the unified SEM, which in a way is kind of the first steps towards the algorithmic approach of GIMME. Right, so this is, I really don't like this. In retrospect, I wish I had used a figure instead. But to fit a unified SEM in the GIMME package, you can see that it's just called InSem. So if you have R and you load your data in, you can fit it that way. But what it does is it starts by initializing, let's just say we take one person's data. We have one person's time series on however many variables. We start by estimating what we'll call a null model. And in the null model, what we free are those autoregressions. So coming back here, we free the effect of each variable on itself to be estimated. And then on top of that, we free the diagonal elements of the phi matrix or the psi matrix, which is the residual covariance matrix. So those are the only things that are freed. And then what we do is we look at the modification indices for all of the effects as being possible candidate paths. And the path that has the highest modification index will be the one that's added for that participant. And the important part here that really is worth taking away is when we set the autoregressions to be true, because this allows us to establish some form of Granger causality. So I'm going to go back and then I'm going to explain this really quickly. Right, so if we just think about a standard regression, the effect of variable 1 on variable 2 is the exact same as the effect of variable 2 on variable 1, right? So it's impossible to distinguish the direction of that effect. You can replace the variables in any way, and you'll always get the exact same association. But when we account for the lagged effect of the variables upon themselves, then this symmetry from A1 or from variable 1 to variable 2 and from variable 2 to variable 1 is broken just enough for this modification index approach to work. In fact, it works quite well, which is really crazy. And so that's really like how we get this solution to finding the directionality, right? So in the past, using the Cholesky decomposition approach, there isn't one identifiable solution. But with this approach, what we can find is that by accounting for the lagged effects first and then using the modification indices, we break any symmetries that exist, and it allows us to pick up the direction of the effects in the contemporaneous matrix. So after freeing up the diagonal elements and freeing up the autoregressions, basically we look at the modification indices. If the modification index is significant for that individual, we'll add it. And then that becomes the new comparison model. Then we look at the modifications again, and then we see, okay, is there another path that we can add? We find the best path, the path that would improve model fit by the most. We add that and we repeat that again and again until we can't find a way of improving an individual's model. And that's basically just how USEM works. And so what you get at the end of the unified SEM is a structural VAR model, which contains the directed effects in the contemporaneous space, as well as the directed effects in the lagged space. And that's pretty much it. I don't know if that's quite a lot. So if anyone has questions, feel free to ask. I know like putting it in like computer science language wasn't helpful, so I apologize for that.
Well, thanks for breaking this down. I mean, I'm used to thinking about fMRI time series as the variables, but like, can you give just a few examples of the different things that can act as V1 and V2 just in like, you know, psych studies generally? Like what are the—
Oh yeah, absolutely.
Make it concrete.
Yeah, so I'm gonna talk about this in terms of like an affect study, because that's kind of what I've done. So we can say that variable one is depression, and I'm gonna keep this like ridiculously simple. So let's just say variable one is depression and variable two is, I don't know, your happiness, right? And so you can imagine that if at the previous assessment, let's say I'm measuring people, I don't know, twice a day, every day, for like a month. And so variable one at time -1 might be my depression in the morning, right? And then variable one at time would be my depression at night. And so we expect there to probably be a positive association. If I was depressed in the morning, I'm probably depressed at night, right? And then let's say this is variable two is our happiness variable. If I'm happy in the morning, I tend to be more happy at night. If I'm happy in the morning, I'll probably be less depressed in the evening as well, right? But when it comes to talking about the contemporaneous effects is where things can get a little muddy. And so we have to keep in mind that this is relative to the sampling interval. Since we're doing this twice a day, and we can just assume that it's equidistant, so every 12 hours. What a contemporaneous association means is within those 12 hours, right? So not from one 12-hour window to the next 12-hour window, but within a 12-hour window, is there an association, right? So it also makes sense that when I'm depressed at variable one, I probably get less happy, but it doesn't take 12 hours for me to get less happy, right? It's pretty instantaneous. Certainly it happens faster than a 12-hour window. And so the contemporaneous effects really help us get at and compensate for the mismatch between our sampling rate and the actual process, right? So when I'm sad, I get less happy almost immediately, right? Like it doesn't take any appreciable amount of time for that to happen. But it doesn't make sense for me to ask people, hey, take this survey every minute of the day, right? Like we would get a lot of attrition that way. So we have to kind of balance the demands of the subjects with the demands of getting the data at the right time scale that we want. And similar with fMRI data is that you can't really increase the temporal resolution all the time, or really like we're getting very minuscule improvements to that kind of temporal resolution. And so when the effects are happening much faster than what we can sample, then you really want to get at those contemporaneous effects. So the lagged effects really kind of serve as a means to getting that information. Maybe they're not super relevant in the context of certain data types, but being able to get that information is super helpful. The other idea, the other explanation that I have is kind of dumb, but it really helped me get this, was the idea of if you measure when your sprinklers turn on every 12 hours, you would find in the lagged context that when the sprinklers are on, the next 12 hours, the grass is not wet. So then you might think, oh, well, my sprinklers don't do anything. Like what's the point in watering the lawn? But it's because the sprinklers have an immediate effect on the wetness of your lawn, not a 12-hour lag. And so it's why it's important. Obviously, if we could just measure at the correct time interval, that'd be great. But given constraints in our ability to do that, there are methodological ways of kind of circumventing that. Did that kind of help? I don't know. I'm sorry I have like terrible examples.
No, this is very helpful because we're just thinking of like we just had a class on ecological momentary assessment where you do get multiple measurements from the same person. So and then we had a class where we talked about Granger causal analysis and fMRI data. So this is all kind of like bringing together a lot of different things.
Yeah.
So
yeah, no, this is definitely kind of like an amalgam of all of those. Absolutely. Let's see. All right, cool. So GIMME. So this is when I said that I wish I'd made a figure. This is a figure that I made, and I should have done that for the earlier one. So if we kind of take what the USEM was for a person, we can extend that to fitting to groups of people, right? And so you can see at the bottom here, eventually we will fit a unified SEM for each person. But the goal of GIMME, as I said, was to find kind of a group level model, right? So the first step is to fit a null model And the null model is going to be defined in the same way that it was for the unified SEM, where we'll have all of the autoregressions freed, autoregressions being the effect of the variables upon themselves, as well as the diagonal elements of the covariance matrix. So those will be the only things that are freed for estimation. And then we check the modification indices again, except instead of looking at it within a person, we look across all people. And then we look at whether a given parameter would improve the model fit for a majority of people. So basically what we do is we look at, when you get modification indices, you can see like the expected change in the model fit. So then we'll sum that expected change. And so across all individuals, and then what we'll find is, okay, this parameter would increase the model fit for a lot of people by a large margin. And then we make sure that it would improve it for some threshold. So earlier I said 75% is the default. At this point, the user could specify any proportion that they want. So if they're like, it has to be greater than 90%, 90% of people have to have this path to be added, that's where you would add it. And so if the parameter would improve the model fit for a majority of people, then they would add that to the model. And then that basically becomes the new null model. And then we check the modification indices again, and then you just repeat that ad nauseum. And then once there isn't a parameter that would improve the model fit for a majority of people, then what GIMME does is it adds this pruning step. So it basically goes back and looks at all the parameters that it added already to the group level model. And then any model that's no longer significant for a majority of people, it'll remove. And the idea is basically like, if I added a parameter at one step and then further on, I add like 3 more parameters, those 3 parameters may have ruled out this other earlier parameter that I added. So the pruning step helps us kind of reintroduce sparsity into the resulting model. And then after the pruning step, we go and we fit the individual unified SEM within each person. And the difference is that the null model for these unified SEMs is the group model that we just arrived at, right? So now everyone has to have the same model going into the USEM step, but the resulting models from there will be person specific. So everyone has the same group structure, and now we'll allow for person specific stuff to show up when we're fitting this individual USEM step. Does that help? Basically, in this example here, going into, so after we leave the group step, everyone has to have these bold black effects estimated. These have to be estimated in their model, but now everything else is free. Everything else can be estimated now. And then it follows the same modification index approach. But when you look at the results from GIMME, what you'll find is that every single person has these autoregressions freed, as well as this directed path from motor to auditory. So everyone has to have that. One like minor point that I want to bring up is that GIMME, unlike say a multi-level model, doesn't impose kind of a distribution assumption around a single parameter. And what I mean by that is, let me go back. I don't know why I keep jumping back. What I mean by that is that when I say that everyone has the association between motor and auditory estimated, that's it. Like everyone just has to have that estimated, but it's not fixed to a particular value. We're not assuming that everyone has a positive association between motor and auditory. Everyone just has to estimate it, right? When we're looking at the modification indices, it's just saying adding this path would improve the model fit. So it could be a negative association for some people. It could be a positive association for some people. It could be really strong. It could be really weak. The only thing is that a majority of people would have their model improved if we estimated it. So that's something to also like keep in mind, is that there's a little more flexibility in how the GIMME model is allowing for structural relations, but it could also not always necessarily be like the way that we think it is, right? Because if like half of the people are positive and half are negative, then we also have something to explain, right? Because we might expect everyone to be one polarity or the other, but that's not the case with the GIMME model necessarily. Okay, so I realized I could have just gone here. So I'm not going to spend too much time on this page because it's kind of overwhelming. But basically, we have what we've done is we've decomposed the A matrix from the structural var. Now there's two parts. There's the group specific part as well as the person specific part. Same with the phi matrix. We've just split it into being a group component and a person specific component. And what the I subscript here means is basically like that this is basically a group path that is imposed, but it's person specific, right? So it's that exact thing that I was getting at, is that everyone has to have a thing estimated here, but whether it's positive, negative, 0.8, 0.2, negative 0.3, it doesn't matter. It just has to be there. Yeah. So GIMME was kind of like the way to go for quite a while. And then Katie published a paper in 2014, and then the more formal algorithmic way of doing subgrouping with GIMME was published in a paper in 2017. I think I cite that here, yeah. And the idea was that, you know, grouping is great and acknowledging person-specific stuff is also great, but within our data, we may have subgroups that exist that we are completely unaware of. And so it would be great if we could access that in some way. And when you guys read the confirmatory subgrouping paper, it's basically this exact same thing, except you have an a priori specification of what your latent subgroups are. So then you can feed a vector that says, okay, these people are in this subgroup, these people are in another subgroup. With the standard SGIMME, we use kind of a community detection algorithm to find the subgroups for you. And this is kind of like my primary area of work, which is also why I gave it a lot of slides. But hopefully we'll be able to walk through this. So in this case, we have a bunch of regions of interest that we're mapping. And then we have a bunch of different individuals who have different paths, right? And then in C, what C is basically what we'll call the adjacency matrix. And I'm going to flesh out what that is so that it makes sense, but just know that we feed in an adjacency matrix that we get from the person-specific networks. And by running a community detection algorithm on this matrix, we can find the subgroups in a kind of an automated way. So the next few slides are literally just me kind of hopefully explaining this in a more simple way. Right, so yes, extend GIMME to conduct unsupervised classification, and the subgroups are identified on the A and phi matrices. So let's see if I have a good example. Yeah, so what I'm going to do is ignore that modularity is a thing right now, and then just end this slide with individuals in the same community will share subgroup specific paths. So these are the green paths in that figure that I keep going back to. So we'll have the black paths as the group level paths, and at SGIMME and as well as confirmatory subgrouping GIMME, this is where you would start to see those green paths emerge. Let's see. Cool. So the first step is to create an n by n adjacency matrix, which I've alluded to. And I said that we basically use the phi matrix and the A matrix to do that. So I'm gonna hop back a few slides and then we'll come back here. So in this case, we have a bivariate system, right? And the bivariate system consists of a matrix of A as well as a matrix of phi, right? So in this case, A is zeros on the diagonal. A1, 2 is the first row, second column. There's an association there, and then there's A2, 1. And then phi is a 2 by 2 matrix. And so if we have this for several people, what we'll have are two 2 by 2 matrices for every single person in our sample, a 2 by 2 A matrix and a 2 by 2 phi matrix. And what we can do is we can look at if I have a path from A1 to, or from variable 1 to variable 2, and if any of you have a path from A1 to A2. And then if we do, then we have one path in common. And if we don't, we have no paths in common. And so we repeat that for every single possible effect, right? And that turns into a count. So then when we go back here, we'll see that the matrix is n by n. So it's person by person. And then a given cell of that adjacency matrix is just a count of how many paths we have in common. And the paths just take into account the contemporaneous matrix as well as the lagged matrix. And what we define as common is that the direction obviously needs to be the same, but also the sign. So in this case, this is where like the sign differences would show up. So if we had a group of people that had a strong positive path and a group of people that had a strong negative path, and that was the defining characteristic of the subgroups, this is where that separation would occur. And then we search through it using walk trap. So I'm keeping an eye on the time, and I might have to skip a lot of the community detection stuff, which is fine. So this is an example of an adjacency matrix. This is simulated data that I made up, right? So we can imagine here we have 8 people, right? Because it's 8 by 8. And what we expect in a community detection approach is that people within a community have more things in common with other people in that community than they do with people outside of it, right? So like I have more things in common with my family than I have with random strangers I meet on the street. And so within the blue box, you see like, you know, these people have 15 things in common, the first and second person. The first person with the third person has 13 things in common, etc. And then within this group, while it's not as high, relative to outside, they're also really strongly connected, right? So this person has 10 paths in common, 9 paths in common, but then like the first person with the last person only has 4 paths in common, right? So they don't have as much in common with people in the other group than they have within their group. And that's essentially like the whole idea, ultimately, of community detection is we should find a way to find groups of people who are really similar. And in this case, what we're clustering on is the dynamics. So people who have a lot of similarities in their dynamics should be clustered together because they tend to have the same model. Whereas people who are in different subgroups might have completely different networks. And so this is kind of how SGIMME is working. I'm looking at time, I'm gonna just skip this, but just know that like basically we use this algorithm called walk trap, and it's fantastic, it's great, it's super cool. We basically just turn the adjacency matrix into a distance matrix. So this is the Euclidean distance of the A matrix. And then we use fancy math. We basically just use Ward's algorithm to kind of do a rational start. And then as we're partitioning the data set, we assess this thing called modularity. And modularity is just a measure, one measure of many that tells us how good are the communities that we're making, how good is the quality of those communities, where higher modularity tends to be kind of more indicative of better communities. And the idea of communities would really just be more paths in common and fewer paths leaving the community. So communities should be really strongly connected to each other, but not to other folks.
Can I ask a quick question?
Yes, absolutely.
I vaguely remember when we were working on this with Katie, something about the number of the nodes being important, like you can't have too many because it can't, there's a limit, right? And what is that limit based on? Like you had an 8 by 8 right there, but what was the upper limit and why is there an upper limit?
So in terms of subjects, there doesn't seem to be a limit in terms of subjects, but the limit tends to be on the data set that you're, yeah. So then like, I think after, if you're going past like 20 ROIs, it starts to take a long time to estimate anything. If and when it does actually get through the 20 node networks, the subgrouping steps are fine. The community detection stuff was developed in like statistical physics, and like they typically use actually like thousands, like an n of like 10,000. So like this step isn't bogged down. It's the fact that like the computation becomes really difficult. So I've been kind of avoiding the really technical stuff, but like since GIMME is estimated using like a block Toeplitz covariance matrix, you basically stack the covariances and you have like a 2p by 2p covariance matrix. And so as you add one variable, you're adding like a 4 more in dimension. And so it gets really difficult to estimate as you're kind of scaling up the variables. So yeah, that is something definitely worth considering, is that if you have a large number of ROIs that you want to study, or just variables in general, it gets really difficult really fast as you go up. Though there is some work being done to kind of circumvent that issue. Okay, yeah, so confirmatory subgrouping is really just one slide. It's all this stuff, except instead of doing this step, the subgrouping step, you just say, I think these people belong in this group. And so if you have this a priori specification of who belongs where, definitely do that. But then if you don't have that a priori thing, hypothesis, also just like, if you're curious, right? Because so SGIMME is definitely an exploratory procedure. It's not a confirmatory one. So obviously in reporting it, you have to be more specific about how you're using these methods. But certainly SGIMME can reveal things, or I think like the biggest realization is that it can show that a group that you might think is homogeneous is actually quite heterogeneous. So definitely explore both. So with confirmatory subgrouping, the difference again is that you supply a vector of just group membership. So you'd say like 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, and then you just feed that into the code. And again, I'll show like how you end up passing this in. And it's really similar. So you fit GIMME in the standard way. Then it puts people into the bins that you place them into. You said these people belong in group 1. And then it acts as if it's basically just starting GIMME again. But now the null model for those subgroups includes the final model in the group search, right? So everyone starts with the group model, and then they find the subgroup paths from there. Let's see. Okay, so href GIMME, basically it's a way of like convolving the tasks with the time scale, convolving the tasks with the time scale of the actual associations that are occurring. So again, the thing that we're adding here are gamma and tau. And what I'm going to start with gamma. So with gamma, what we're looking at is the effect of the task. So this is for event-related data. So it's the effect of the task on the particular regions of interest that you're looking at. And then for tau, these effects are going to be kind of, you can think of these as like moderating effects. So it's going to be whether the task kind of moderates the association between two ROIs. And then let me see if I could just pull up if we have that. So I'm gonna try something. Did my desktop switch? All right, sweet. So this is, so again, this is at the end of the presentation, but just to show kind of more concretely. Oh wait, no, I have this at the end of the slide, don't I? Yeah, okay, never mind, I'm stupid. So what we can see here is that when we're using href GIMME, you can see the effect of ROI3 by task. So this shows that ROI3 does have an influence on ROI4, but that effect is modulated by the task, right? And then you can also see that there's task-specific effects on the ROI. So the specific part, the contribution of href GIMME is that it allows us to convolve the tasks and see, kind of match it up with the time scale of the tasks being done. And then you can look at the effects of those tasks on the regions of interest, as well as their modulating effects. Right, I think that is use ROIs passed into href GIMME. Yep, smooth finite impulse response functions, and then href. Yeah, so one other thing to note here is that when href GIMME is searching for like kind of the appropriate hemodynamic response function to kind of fit, it's fitting it as a person-specific href, but it's not ROI specific. So basically, it looks at all of the ROIs for a person, and then whichever href kind of accounts for the greatest degree of variance, then that is set as the href for all the ROIs, and then it's passed forward from there. I think there's some work being done by Kelly Duffy, who's at Minnesota now, to extend this to be ROI specific hemodynamic response functions, but it gets really hard, at least from when I was reading the paper. It gets very complicated to do that for ROI specific stuff across all persons in the data set. So definitely reach out to her if you're interested, because she definitely knows more about this than I do. But then following the creation of those variables, the task specific and the modulating effects, it's really just standard GIMME after that. So if you have a good handle on, let's see, if you can get a good handle on this algorithm, this really is kind of, at the end of the day, when we add subgrouping, what are we doing? Where we say fit individual USEM for each subject, we do community detection, and then we kind of do this again, right? And then when we're doing the confirmatory subgrouping, we're adding a step in between here to just split people, and then we repeat this whole step again. So really, like, everything follows the same general logical structure. It's just with some gigantic chunks of code in between. Does anyone have questions so far? I have a couple concluding slides on like stuff that we're doing now that seems really cool, but I know this has been a lot.
This has been really helpful. You know, I really like the way you really laid this out and, you know, made it seem so much clearer. I was wondering, and I may have just missed when you described this, but in the step where you're checking the modification indices, can you describe a little bit what those look like, what those are?
So you're saying when we're looking at the modification indices?
Yeah, like what are you actually seeing there?
So when you run it, you don't actually see any of this happening, but what the modification indices are, they're Lagrange multiplier statistics. So if you run like any classic sim, what you can do is you can fit it and you can request the LM stat. And basically what it is, it's basically saying, given the model that I have now and the parameters that I've constrained to be fixed or to be 0, if I freed some of those parameters, if I freed each parameter just one by one, how much would the model improve, right? So then I would get 5 modification indices for the 5 variables that or 5 effects that I have fixed. And then what GIMME is doing is it's looking at each of those and then it's saying, okay, the third one seems to improve the model the most. So then it frees that up to be estimated. And so then when we're doing the group search, it's kind of looking across every single person on all those 5. And then it's summing up how much would the model improve for this person and this person again and again. And then once it finds that parameter that would improve it for the most people by the most amount, then that parameter would be free. Does that help?
Yes, that's very helpful. Thank you.
Yeah, no problem. Anyone else? Right. So this is like speculative work. This is like really stuff that I'm doing like right this second in terms of, I'm calling it fuzzy GIMME. Really, it's more general. I'm not staying in the GIMME framework for this one. So in a perfect world, everyone would fit into a category, right? So that'd be fantastic if there was no ambiguity as to where people belong. The yellows belong with the yellows and the blues belong with the blues. But real life is not that way in like almost any field. And so some work that I've been doing has been looking at like, so again, I study suicide, so it's arguable how relatable this will be. But the idea is that we tend to draw this boundary between people that ideate on suicide and people that act on suicide, as if there's just some discrete switch that goes off on someone's head and they're like, I'm going to kill myself. But in reality, that's probably not the case. It's probably the case that there's some gray transition area as one person moves from one area to the other. And so the idea is to draw from the fuzzy community detection literature, which is in statistical physics, which basically says, what if instead of saying that you are in the green group or you are in the blue group, I say there's a certain likelihood that you're green and there's a certain likelihood that you're blue. And so in some cases, I can be 99% sure that you're green. But then in some cases, we might find people that have kind of an equal likelihood of being green or blue. And in those cases, I'm arguing, that we might be able to find interesting things from studying those ambiguous people, those people that don't really belong to a community strongly. So some work that I've been doing on this looked at affect data for a group of people with major depression and controls. So even though I'm showing a bivariate association, this is actually on 14 dimensions. So you have to kind of, nobody can imagine 14 dimensions, but we could just pretend. And what we found is that this group of red dots are folks who are in the control group. Every single person here is a control person. And then these weird like teal light blue people are strongly depressed people in the major depressive group. And one thing to note is that the depressed group are folks who are undergoing outpatient therapy. So the hope is that they're improving in some appreciable way. And so when we looked at the fuzzy people, the people who did not strongly move in one group or another, is that all but case number 39 are depressed people, or people who are diagnosed with depression, but their dynamics seem to be more similar, or kind of like less conclusively depressed and almost control in their across 14 dimensions. And so the idea that I'm arguing is that it's not necessarily going to be super useful all the time to study the people that are absolutely conclusively depressed, as well as the people that are absolutely conclusively controls, but rather that there's something to be gained by studying the people in the fuzzy space. And so how this relates to everyone's work, I'm not sure, but it's super exciting stuff that I'm excited to be writing about.
So we have at least a couple of clinical psych students in this group, so it probably relates at least. But you know,
I hope so.
Yeah, no, a lot of us are working on sort of looking at transdiagnostic features in neurodevelopmental disorders. So this is, I mean, it's a problem with anything in the DSM where the categories are not so clear cut. So, I mean, I can see this being super useful. With the 14 dimensions, would you mind telling us a little bit about what other things are?
Yeah, so these are like 14 affect dimensions.
Okay.
So yeah, they're all arbitrary, and some of them are like kind of weird with like enthusiasm and differentiating that from happiness. But the fact is that like, so one thing that I want to note is that like, if I just said there's two groups in this, the black dots would be grouped largely with the depressed group. But then if we look in terms of the quality of the solution, in terms of the model fit, it's actually worse than the fuzzy solution. So it's that these fuzzy people, which sounds almost offensive, so I don't know how to like phrase this, but the people that don't have like a firm category don't belong together. Like I can't emphasize this enough, is that they wouldn't form a cohesive group. So they're all different from each other. So the thing that they have in common is that they don't fit in with any of the groups. So the next steps that we're looking into is how do we study these? Because if we can't use like a GIMME approach, because we can't assume that there's a commonality because they're not being grouped together. But yeah, no, absolutely. The in terms of psychopathology stuff, that's actually what sent me down this rabbit hole, is that while I'm looking at this in terms of the person by person network, we can also look at the symptom network of people. And so what we would see instead of a person by person network, it'd be a symptom by symptom network. And if we have fuzzy symptoms, the idea is that the connections, or the symptoms that are fuzzy are the ones that help propagate and connect multiple psychopathologies. And so if we have a bunch of symptoms or a set of symptoms that are fuzzy, those are probably the ones that help move you from, say, like a depressive cycle to an anxiety cycle, where the activation of those fuzzy symptoms is what kind of kicks off your comorbid psychopathologies.
Do you think there's a prediction that like the fuzzy dots are the ones that are harder to treat because of sort of not falling into a traditional, I don't know, categories, or, well, actually, they're not diagnosed as depressed, right? In your example.
So these folks are diagnosed with major depressive disorder. The argument that I'm making is that since they're kind of in the space between the controls and the solidly depressed folks, is hopefully that the outpatient therapy is helping. It'd be great if there was a way to test this, but my proposition is that these folks, the black dots, are moving towards the red space to be more like the controls. Because at least like, since all but one have a diagnosis of MDD, it'd be weird if they're moving towards the the solidly depressed group. So hopefully they're moving in the positive direction. But again, like, who knows?
Great.
And yeah, so that's kind of like what I did prepare. I know that I can totally stick around for a bit after your break and answer questions as well. And then I can send these slides over if folks want them.
Well, thank you very much for putting together these slides and spending all this time. I don't know if folks want to do break then question, or it depends how long you can stick around, Jonathan. We don't want to keep you too long, so it's or we could do questions then break. It's up to you folks.
What do you
Yeah,
guys want to do?
Totally fine.
I think we're gonna have to make a call. Everybody's shy. Lucina, call it.
Call it. Well,
Break.
you guys wrote questions in the forum, so you can, feel free to ask I mean, we don't often, or sometimes we get the speaker to stick around, but we don't always, so we appreciate it. But we don't want to keep you forever either. So if there's any questions that you put in the forum that were like, we could ask while we're right here together, that would be great. Can you guys see the forum questions? I think that the talk definitely made a lot of things clearer, so maybe some things were already answered, but feel free.
I had a question about confirmatory subgroups, GIMME. So I'm in a statistics class that just started talking about multi-level modeling, so I'm thinking a bit about like longitudinal investigations of whatever, like functional connectivity or activation and whatnot. So I was curious about whether this confirmatory subgroups approach could also be used to study like multiple observations in the same participants, where each subgroup represents a different time point in your longitudinal data.
So, right. So this relates to a conversation I had with Peter a little while ago. So there's no reason why you wouldn't be able to treat a different segment of someone's time series as a separate person, if that makes sense. I think that's what you're asking. So then, like, if I measured myself like 1 year and then I measured myself the next year, and then treated myself as two different, and I treated myself as like a different subject, you can absolutely do that. In fact, that's like a way of testing for stationarity. Basically, like, one of the assumptions of time series analysis is that you have like a weekly stationary process. And that's basically like that the process doesn't change over time, right? Like, so the effect of A on B doesn't change across time. And so when you model yourself, so to speak, as two different subjects, if you do find subgroups, then that would be indicative of the fact that there's some change in your dynamics over time. So you absolutely could do it. And then, like, in relation to MLM, the difference is still going to be that with MLM, you still assume that there's a fixed parameter structure, right? So like when I get a multi-level model and the results of it, what we're assuming is that every single person has that same set of connections, right? So even if you have random effects about those parameters, everyone has that connection. Whereas with the GIMME approaches, some connections are forced to be estimated for every single person, but then those aren't constrained. But then on top of that, we also have that the individual specific parameters that are being estimated that don't have to be shared. So there's like a give and take. In a paper that we're working on right now, we call it like the idiothetic kind of paradigm. So it's kind of like, how much do you want a group level structure versus how much do you want an n equals 1 structure? So it's really about like finding your place in that spectrum. So with MLM, you have kind of a more fixed, everyone has the same kind of model. Whereas with GIMME, I would say we're closer to like this end where you have some group parameters, but not all of them are fixed.
So,
I don't know if that was like a answer.
no, yeah, it definitely was. So then if you do use the GIMME approach for that research question, is the main drawback that you don't necessarily have as much power to control within the individual?
So you can, in the GIMME syntax, you can estimate specific subject level paths if you wanted to. So you can have as much control as you want. But once a group level path is estimated, then yeah, that's going to be forced on every single person. I don't know if that's.
No, yeah, I think that answers my question.
Okay, yeah.
Thank you.
Yeah, no problem.
I think I have a follow-up to Lauren's question. First of all, thank you for this talk. It was super clear and made everything much easier to understand. But one of my questions was, if you are doing like confirmatory subgrouping and you have like subgroup specific edges, I think in the paper that we read, they talked about how one limitation is that you can't really compare subgroup specific edges between subgroups, but could you, like in this iterative process, like constrain everyone to estimate like a beta weight for all subgroup specific paths so that you could facilitate between subgroup comparisons in that way?
I would have to check what they're talking about in that. But yes, so assuming it wasn't fixed in the group, you're saying that if you wanted to have, are you saying that you want a fixed value for the parameter or just have that parameter be estimated for everyone?
Just have it be estimated for everyone.
Yeah, so in the GIMME syntax, let me see if I can find like a simple example. But yeah, so when you're writing your GIMME model in R, which I should probably go over that. That would be probably useful. So GIMME accepts both, and I just sent the email with my slides. So then if anyone wants like this tutorial website, it's at the last slide. When you're preparing your data, you can have a folder that has a CSV where the CSV for each person is the number of rows is the number of time points and the number of columns is the regions of interest that you're studying. And you would have n CSV files, right? So you'd have as many CSV files as there are people. And then you can analyze the data that way, or you could read it into R. If you have MATLAB, there is a MATLAB version as well, but don't ask me about it because I have no idea how it works. And when you're running GIMME, basically you have your data. And so the data will either be, where is that directory, or where is what is the object where your data are stored in R. Out is just where do you want the data saved to. Separating is basically if you used a directory, then you need to say like, what are the files? In this case, if you're using CSVs, the separation would be a comma. Header true, AR true. Okay, this is actually not that useful. Let me find yeah, so there's an argument in GIMME called paths. And so when you're specifying paths, the way it works is, I know that the latent variable has it. So it's very similar. I don't know if anyone here has used Lavon, but basically you would have paths here, and then you could specify the paths that you want to be estimated. So if you want this lagged effect estimated, you would just name it after the variable names. And then you would just force that to be estimated. And you can either estimate it across all people, you can make it so that it's not estimated for anyone, And you can also fix it to be estimated at a specific value if you wanted to. Yeah, so you have quite a degree of control because the basis of our GIMME is Levon, and Levon has just a lot of flexibility that way.
That's helpful. Thank you.
Yeah.
Any other question? Jonathan?
So we can give you a break since it's probably late in the day for you, Jonathan.
Oh yeah.
So thanks so much again for joining us and for the great presentation. We'll, if you don't mind, we'll take your slides and share them with the class as well. And
That would be
and hopefully we'll have some opportunities to play around with GIMME at some point
Yeah.
in the near future.
Yeah, absolutely. Thanks for having me. And then for anyone, if you do have questions that you want to like follow up on, or if you choose to use GIMME and you need help, feel free to like reach out. I too am a struggling graduate student, so I know what it's like. So yeah, feel free to reach out at any time. And thank you again for having me.
Thank you so
I
much. This was
appreciate it.
great.
Thank you so much.
Yep.
So I'm gonna stop the recording.
Bye, everyone.
Bye.
And, we can
Do a break.